Okay, so welcome everybody to a slight delay in our first session of the day, multimodal dynamical gestures. Our first speaker is Nobuhiro Furuyama from Japan, who will talk about coordination among articulations, gesticulations, and breathing movements in case of articulation of a and flexion at the wrist.
Good morning, everyone. I'm Nobu Furuyama from National Institute of Informatics in Tokyo. And you see the title here is a little bit different from the studies reported here is a collaboration with Hiroki Takase, he's a breathing movement guy, and Koji Hayashi. Before we move on, I have to confess that I'm pretty much new to the type of experiment, the type of analysis that I'm recording here. So I really, really appreciate any comment, any critical, but frankly, comment on those. So this is the outline of this presentation. We are interested in determining information specifying both intra and interpersonal coordination in speech and gesture from an ecological perspective and a dynamic approach, with a special focus on coordination around articulation, gesticulation, and breathing movements. Why breathing movements? Well, it's, for one thing, a subsystem, a direct subsystem of articulation, and it's also a subsystem of gesticulation, although the coupling is sort of remote, link articulation. So here's some background on the study. Speech and gestures are said to co-express similar or related aspects of one and the same state of appraisal with things. This is basically exactly the study of discursive structure and how the gesticulation compares to the structure of discourse. And why can we say that? Well, because they have a particular spatial relationship with each other. In other words, it shows the speech and gestures show the particular coordination pattern in the discourse. So I was working on how the way in which speech-gesture coordination contribute to the structure of the discourse in my previous works. I'm now more interested in how the coordination is made possible. One of the theories goes like this. This is a sketch model of speech-gesture production, and the module here is a pin-leveled model of speech production. And pin-level is the guy at the Maxwell Institute of Netherlands. And his student, the writer, added the gestural modules, which doesn't interact with the linguistic module here. So everything decided here is only executed in the following processes sometimes to do that. And this is basically a version of classical model theory in that the parameters are all planned in the system, and then such a plan is carried out by executors. But there are some interesting phenomena, speech gesture phenomena, that's been reported recently. Speech and gestures are coordinated not only interpersonally but also interpersonally. And this is an example from the previous work. What they're doing is this person is learning how to make a balloon origami from the person on the right. And what's interesting is that she's producing a lot of gestures, sometimes with her own speech and sometimes without her speech. Gestures without her own speech typically coordinated with the speech gesture by the instructor. So that's the case of the interpersonal coordination of speech and gesture. I wish I could be actually creative, but I don't have some kind of chance. And this is challenging for the classical model theory or sketch model of speech and gesture production because it involves at least two brains and bodies for which no physical organ of control can be identified. Here's another interesting case, and there's a case of Ian Warren, if you're familiar with the book entitled Pride and Daily Mapping by Jonathan Cole, actually he's sitting here. And Ian Waterman is the person patient who lost all of the haptic perception from the neck down, but fortunately spared all of the cognitive functions above the neck and motor control systems. So he doesn't know where his limbs are, and all of the emotions are guided visually only. And that holds for the speech gesture coordination. He produced a lot of gestures while he's speaking. And speech gesture coordination for him is perfectly natural under visual conditioning. And this is, in a sense, similar to interpersonal coordination, in that the coordination is mainly achieved by the visual guidance, although he only has one brain. So the question is, what information is applied in coordinated speech and gestures, both intra and interpersonal coordination? And are breathing movements involved in speech gesture coordination? If so, how? These slides just describe what we learned basically from Nobu. Right? So allow me to skip those slides to save time. So based on the ecological and dynamical systems approach in particular, we have conducted some experiments, and we're going to talk about just three. The first one is interpersonal coordination of movements and breathing movements, and the second is the interpersonal coordination of the same movements. And the third one is interpersonal coordination of articulation, gesticulation, and movements. I'm going to talk about experiment 1 and 2 very quickly, so that I can have more time for experiment 3. Here, what the subject does is this. In phase mode, he has an inverted pendulum, and when he does the lunar flexion, it coincides with the acceleration. So, and when he does the radial flexion, it coincides with the in phase. That's in phase. So it goes like something like that. And antiphase is just the opposite of that. So it goes like something like that. And the question is, what happens if the frequency increases? We use 3 types of pendulum. One is short, one is medium, one is long. And the frequency that was covered was from 1 hertz to 2 hertz. And it increases in increments of 0.2 hertz. And there are 10 pulses for each frequency. And this is an experimental setting. I don't talk much about this. But the result is basically repeats what have been found for the internal movements. You see the these are percentages. You see the phase transitions for short pendulum and phase transitions for medium and silent pendulum. And not surprisingly, SD5 looks like this. This one is SD5 for antiphase, and this one is the in phase. This is mean pi, arranged by the length of pendulum and as well as frequency, surge frequency. So the impact of the increase in frequency on the coordination is different depending on what type of pendulum you're assuming. So that's the basic premise for the experiment. And basically, in the interpersonal version of the coordination, repeats the same thing. We'll talk about the situation in which the experiment was done. This guy to the left does the breathing. So he goes like, and the sound of the breathing is picked up by this microphone. It's sent to amplifier here, and then to headphones, through which this guy listens to the noise. And according to the noise, coordinating with the noise, he does the pendulum movement like this. And this guy, looking at this pendulum and coordinating with that pendulum movement, he does breathing. And the overall pace is paced by the metronome pulses emitted by a PC. So that's the experimental setting. And basically what you are looking at is the same thing. Critical point is a little bit different. Phase transitions starts earlier than the interpersonal version of data. But the rest of the results basically would be the same thing. So to wrap up the experiment 1 and 2, because although the strength coupling between the two kinds of movements is not necessarily the same as the interpersonal coordination, the principle in organizing the coordination seems to be qualitatively the same, and that is self-organizational, regardless of whether the coordination is achieved interpersonally or interpersonally. So let's move on to the experiment 3, where we look at the intrapersonal coordination of articulation, gesticulation, and breathing movements. Well, to anticipate the results, I should say life is not easy. Well, let me start with the purpose of the study. To examine the stability, the purpose of the study is to examine the stability and variability among articulation of actually it's elongated something like that. And wrist movements, we request the pendulum movement, wrist movements, to be more realistic as a gesture set. And breathing movements. So what the subject did was this, in in-phase mode, it goes like this, flexion and articulation, like and the antiphase is just the opposite. As we change the metronome program, we got this table here. F1 corresponds to 0.59 hertz, F2 0.72, and so on and so forth. And each frequency was repeated 10 times. 10 students, 5 male and 5 female, participated in the study. And as I said before, excuse me, life is not really easy for me because we found some cases of phase transitions in in-phase mode. To go further before, this definition of phase transition here. We define phase transition as the jump of relative phase that exceeds 60 degrees, which does not come back to the original current within 5 movements. That's our definition of phase transition here. Here, it has the jump exceeds more than 3 radians, and that's what we define, how we define the phase transition. Here, we also observe the examples of what can be called prolonged phase transition. So the phase lag is getting larger and larger and larger as the trial proceeds. And this is a table showing how much time do we have? 5 minutes. So we have 5 phase transitions for in phase to end phase, and 9 for anti phase to in phase. And also prolonged phase transitions, we have 3 for in phase and 1 for end phase. And this actually is consistent with the SD5. We excluded all of the phase transitional data from the statistical analysis, but what you're looking at is pretty much consistent with the phenomenon of phase transitions, because SD5 for both in phase and end phase goes up to it, right? So that's one of the things that we can discuss later on. But focus on the shift here of SD5 is occurring at around F4, which corresponds to approximately 1.2 hertz. And something interesting is happening around that area, actually between F1 and F5, and that is the intersection of mean 5 for in phase mode and mean 5 for anti-phase mode. And we wonder why this is happening. If you look at the data for breathing movements, this is means of SD5 side being defined as a phase lag between breathing movements at the chest and the wrist movements. And the data is managed by the local phase mode. So if this is not actually try it, phase mode will try. What this graph says is that the breathing movement, or the relationship between breathing movement and the hand movement is more variable for the in-phase mode of recognition than anti-phase mode of recognition. If you look at the raw data, these are some of the examples from in-phase mode that we started. Around F4, you can see the subtle difference in the way in which breathing movements are organized. This represents chest movements, this represents abdominal movements. So chest is here. And the pattern is gradually going down. And as the graph goes down, the amount of the gases left in the lung goes down as well. So there's not so much gases left in the lung. And at this point, the subject seems to change the strategy of breathing movements. So the left amount, the amount of gas left in the lung goes up gradually, goes down gradually, and that repeats that pattern over and over again. This guy has a different pattern. It's in a sense, breathing movement seems to be very flexible and very free from the coordination of speech and gesture. But here, it's got a rhythmic structure like this, very regular in a sense, and so on and so forth. So it seems to me that the breathing movements, the way in which breathing is organized, seems to be changing according to the way in which speech and gesture are coupled together. So that is the basic finding that we have been observing. Nothing is conclusive yet, but it looks like the pattern of breathing movements seems to change together with the changing the way in which speech and gestures are coordinated. That's basically it. How many minutes do I have?
For 30 seconds.
Oh. Let me go back to the phase transition because from in-phase mode and anti-phase mode, because it's here. After Professor T.C. Chan's talk yesterday morning, well, my definition of in-phase mode is depends on the type of muscles that is used. It's homologous. But in another sense, dynamical speaking, if you go like this, concentrate movement should be like this. So this should be more stable, right? So in terms of that kind of dynamics, my in-phase mode here can be defined as antiphase, and antiphase being in-phase. It's only in terms of homologous, the type of muscles that is used, that we can define this type of coordination in-phase and that type of coordination as antiphase. So that would be one of the things that we can discuss later on. Thank you.
I have one question, Mike.
I think the problem with the data is that once the detuning term is other than zero, and you have two oscillators that are not contributing equally to the coordination, then the particular bifurcation is a saddle node bifurcation, not the one that gives you an abrupt transition. It gives you very gradual transitions, and it's a situation where both antiphase and in-phase can, at some frequency, become annihilated, essentially. They leave ghosts behind, they leave ghost attractors. So I think the data you're seeing are really reflecting the fact that you're looking at, in quotations, phase transition of a kind induced by a saddle node bifurcation, and you're not going to see the clean pattern that you were expecting. It's just not going to be there. It's a different dynamics.
Thank you very much.